So you can start the program. Good evening. Welcome to the second day of our lecture series. Uh, Today we will hear about the very important, concept on emerging technology, that is the machine learning, from our very knowledgeable speaker, Dr. Amritendu Mukherjee. Before that, let me tell you a little bit about him. Dr. Mukherjee is a technology leader and AI research scientist with 15 plus years experience, spanning the productization and the commercialization of the advanced technologies. He holds a PhD from the Indian Institute of Science, Bangalore, with a primary focus on the application of advanced machine learning, deep learning algorithms, and statistical learning theory. His expertise spans over the uh, deep generative models like the LLM, large language model, SLM, DDPM, GAN, model compression methodologies for the edge deployment, and explainable and responsible AI. So hopefully we are going to listen a very enjoyable lecture. Before starting, I want to mention two things. First thing is that all the lectures of our lecture series will be uploaded in our on our MAKAUT YouTube channel, online MAKAUT. For example, actually yesterday's lecture also we uploaded in our YouTube channel. So I request to you that please subscribe the channel. And second thing is that we will provide the certificate, because actually number of participants actually asked me about that, and we have decided that we will provide the certificates and what's the criteria for getting that. Everything mentioned in your dashboard. So whenever you log in into your system, at the bottom of the dashboard, you will find what's the eligibility criteria for getting this certificate. Okay. Now I request you to all that keep the microphone and the camera switch off during this session. And after the end of this lecture, there will be a question answer session. So if you want to ask the question, please raise your hand and ask the question. I will select one by one, that means sequentially. Okay. So now I request our today's speaker, Dr. Mukherjee, to start his session, because already 5:13. So, sir, please start.
Thank you, sir. So yes, thank you. This is a very kind introduction. Um, so I'll primarily kind of have three sections, and each sections I'll take kind of we'll have kind of one pause after we complete each section. So the first section I will try to cover the basics of machine learning. And then in the second section, where I'll primarily talk about kind of regression model, the classical machine learning methodologies, regression model, support vector machine, support vector regression, as well as the artificial neural network, but shallow neural network. In the second part, I'll talk more about the deep neural network, and of course its algorithms. So coming from the convolution, then deep generative models, of course transformer architecture, etc. And the third one will basically talk some part on the kind of responsible AI, right? So that's broadly the session plan. And after each sessions and all, maybe kind of we can have a kind of question answer session. Or in between also, if you have any question, please feel free to ask. Okay. And just let me know if I'm audible, and kind of I'm sharing my screen. If you can see my screen.
Yes, you are audible.
Okay. Okay. Thank you. Good. Um, can you see my screen?
Yes, yes, yes.
Okay, perfect. Yes. So the first part is that what is machine learning, right? So the broad idea is, of course, you have certain input features, and of course, you have you try to understand the or try to understand the output, right? Now, this understanding can be many ways. Broadly, like I've tried to kind of break down to kind of there are three questions which you try to ask, right? It could be more also plus minus here and there. Broadly, what is prediction, right? Now, prediction can be in terms of regression. If you want to predict a continuous value, then that's a kind of a regression problem broadly. It could be also a classification. So basically, you want to predict like a kind of say the set of input features, particularly what class they belong to. So that's a classification problem. It could be a generation also. So what broadly the generation problem is that what you nowadays known as Gen AI. Problem is here that you see a set of data and you try to understand that the underlying distribution of the data. If you want to, if you can understand the underlying distribution of the data, then you can generate from this data basically. You can sample from the data, right? That's a generation process. So there's a generation, and then of course, is a recommendation is another set of problems. So let's say if you, I'm pretty sure you all of you have Instagram or kind of any other social network account, LinkedIn or Facebook, etc. Or you watch movies in Netflix and all. So if you watch a movie, you'll always see the kind of recommended movie and all, right? So how the recommendation engine works. Or Spotify, you listen to a music, so and Spotify recommendation is actually very good. So let's say you kind of listen to a music and it will try to recommend you the other music and all, right? So how do they do that? Okay, so there are a lot of math, but I'll try to kind of show you kind of some of the explanation and all, so that you will understand what is happening here. So the idea of linear regression model is y given x, where this x, of course, is a set of input input attributes, and so the assumption of linear regression model is that y given x is a Gaussian distribution of beta transpose x and sigma square. What does it mean is that there will be a linear combination of beta naught plus beta 1 x1 plus kind of up to k. So I'm assuming there are k attributes. So bk xk and then sigma square. So what it means by that is that expectation of y given x is beta transpose x, right? Now, this is where we want to model, right? And the variation is sigma square. Now, variation part we will not be able to model. We will not be able to model. We mentioned that it's an underlying kind of a natural kind of variance in the process. So we don't. Our focus is to model this part, okay, in the linear regression part, right? Now, in a slightly kind of if you think about it, right, what you say is a kind of so that if this, or you can think about from here, so y given x is a Gaussian these things, which means that the PDF will be having a this form, okay. What it also means that, so if you have a likelihood function, what it is actually that it's a kind of let's say you are observing all the data. So what is your probability to observe all the data at the same time? So this is, let's say this is the probability of observe one data, right? So let's say you are observing n number of data at the same time. That means so this should be multiplication of all these probabilities, right? Now if you do that, so then this is basically exactly that, right? I will 1 to n.
Excuse me, sir, your presentation is not visible.
My presentation is not visible. It is visible, no? It's not
Yep,
coming.
it is visible.
Yes,
They
it is
Prakash
visible.
Pahari. Yes, it is visible.
Okay.
If not, then you actually, the Prashad Pahari, please log out and again log in.
Okay,
Yes.
okay, thank you. Yes.
Yes. Please kind of let me know, okay, if there is any issues and all, technical issues and all. I have to kind of go through this math and all, but I'll show you the demonstration, which will be kind of much better explanatory. Now, so the idea is basically you see all the data points together, and then your likelihood function becomes a product of all these individual PDFs of the data points, right? So that's what here it is, as you can see. Sorry, 1 second. Yes. So this is exactly what it is, and then we do something called log likelihood, because if you see a log x function is basically a monotonically increasing function of a particular function in a positive domain. So if you do a log likelihood, so then basically log of this, so that means so log of a product will become a sum. That's what is happening right here. Now, so you want to estimate beta. The problem is you want to estimate beta in such a way that it maximizes your probability to observe this. That means you want to maximize the log likelihood function. Okay, that means you want to maximize this function. Okay, now you want to maximize this function. That means you want to minimize this. Minimize this means the last part of this equation, right? So that means yi minus beta transpose t xi whole square, right? This you want to minimize. So
Excuse me, sir. Actually, Pritimoy sir, please take it in because so many student candidates are not visible in this PPT,
not able to visit, not able to visit, not able to see.
and that's why so many
Oh,
candidates are already mentioned in the message.
okay.
Yeah, I see that. But I see that there is no problem, na? Janun,
Sir, one thing you can do, sir, actually just see some moving the pointer sometimes. So that's why we are checking it's happening or not. Please move your pointer or mouse. That's why you can.
Okay. No, okay. 1 second. Let me share again. Let me share again. No problem. Visible now?
Yes.
Okay. 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 So I was here. Okay. Okay. Yes. So where I was is that, so in the regression function we want to maximize the log likelihood. Not only in the regression, in the machine learning also we'll see most of the cases. So this is our likelihood function, and this is our log likelihood function, and we want to maximize this log likelihood function. Okay, this is called also maximize likelihood estimator. We want to maximize this. That also means that we want to minimize the last part of it, right? Because first part is minus n by 2 log 2 pi by e, or minus n by 2 log sigma square. As I told you, the sigma square we don't want to model. We are wholly kind of focused to model this beta part, because sigma square is the inherent variability in the process, so we don't want to model that. So then our focus is only on the last part. So, and as you can see, there is a minus sign here. That means if I want to maximize this, that means I want to minimize this part, right? That means so that means that I want to minimize this part, right? Yi minus beta transpose xi whole square, right? Which means that, I mean, now how do we minimize? So basically the minimization of this thing is that you take a derivative of it, right? Now that means in a multivariate calculus, that the operator is basically a Nabla operator, and we are doing it with respect to beta. Now beta, remember, it also would be like there will be kind of k betas, right? Because there are k attributes, right? So now if you go ahead and do that, so this beta hat MLE would become, and if you do this calculation, it will become that x transpose x inverse, then x transpose ty, right? Now similarly, if you do for the sigma square and all also, then you can derive that sigma square MLE would become the next one, right? 1 by n y minus x beta MLE transpose y minus x beta MLE, right? Now, so 1 second. So sorry, think I disconnected. 1 second. Yes. Now, just a second. I'm having a connectivity issue here. Just a second, please.
Chandan, please, Chandan Sinara, please mute your mic. Yes.
Okay. Now, we can also show mathematically that beta MLE is the beta UMVUE. What is UMVUE? Is that uniform minimum variance, uniformly minimum variance unbiased estimator. Okay, that means whatever how many estimator we might have, we might have many estimator, but among the entire estimators and all, this will have the minimum kind of variance. Okay, and also this is the unbiased estimator. What it means by that is that expectation of beta hat is actually beta hat. Beta. This expectation of beta hat is beta. That's the unbiased estimator, as well as that it will also have minimum variance. Okay, and we can prove that. However, for sigma square UMVOE is SSE by kind of n minus p, as you can see, where SSE is actually the earlier one, so which is basically y minus x beta hat transpose to y minus x beta hat. Okay. Now I'll just show you some demonstrations, and that would help actually. Now let's say there are some of the data points here. Okay. Now, can you see? This is visible, right?
Yes, visible.
Okay.
Yes, sir. Yes,
Yes.
sir.
Yes, yes. I'm sorry, I might ask and all because I'm not very sure. Sometimes there are disturbances from my side, sometimes from your side. Yes. So, so let's say these are some of the data points, and we started from, of course, we started from some random point, right? And our idea is to get the kind of beta. As you can see, there are beta naught, which is basically beta naught plus beta 1 x1, and there's only one variable, so it is easy. Now let's say I start to kind of train this model, right? So as you can see, and this is my loss function, right? So as you can see, right? Right. So the loss function coming down is supposed to be, right? Right. And as you can see, now it is saturated. Yes. Sorry. Okay. So loss function is coming down, and now it is saturated, and you see that there is no further learning, very less learning, right? That's not right. So what it is trying to do is, it is trying to reduce this error, right, from these data points, right? If I go up, you will see it is trying to reduce kind of this error, right? So if you see, this is the error, which is basically this is error square, of course, right? So that's what it is trying to kind of reduce, right? So this is the error. This is the data point. So this is yi minus xi. Let's say x beta. So yi minus this point is beta transpose xi. This is of course your actual yi. So yi minus yi hat is beta transpose xi. And so this square is trying to minimize, right? If you go here, right, and if you kind of see these, right? So this is what it is trying to minimize is, sorry, this, yeah. So it is trying to minimize is exactly this function, right? Yi minus beta transpose txi, right? Is the last part, right? That's what it is trying to minimize, right? Coming back to here, that's the this is what it is trying to minimize, right? Okay. Now, if you see, right, this will be the case where if you increase it and all, so if you see the bias, if you reduce the bias, it is the errors are increasing, right? You increase the This is also increasing, right? You see, so somewhere in here you get minimized, or sometime maybe here. Yeah, you can see how these things are getting changes. If I do this, let's say now this is like error this thing. Now if I change the bar, it's automatically coming down, right? Yeah. Right. Okay. Okay. Understood how the things work. Now, before I kind of move further, the way we update this is something called gradient descent. Okay? Uh, because you normally, may not be able to. Here I have do it analytically. What I mean by that is that I basically kind of did a differential this thing. I took a grad, right, with respect to individual betas and all, and then I kind of do that. But um, I mean, that's a way to do it in multivariate calculus, but in computer and all, you might not be able to do that. Okay, so all the time. So how do you do it in um, in a computer and all? We do it in a very different way. In a slightly different way, we call it gradient descent. So let's say any parameter, which is theta, right? And the theta update rule is very simple, which is theta update is theta is equal to, let's say, theta I plus 1 is equal to theta I minus del L del theta, right? Which means I just show you this thing so that 1 second. Let me see if I have a gradient descent thing, right? So 1 second. Yeah. So the idea here is that you have this loss function, right, which is um, mm, so your loss function is this loss function. I'm sorry. Your loss function is this loss function, right? Log likelihood function. That's what you're trying to you're trying to maximize this, and then that means that you want to minimize this. So the loss function is minimize this yi minus beta t xi squared. That's your loss function. Now that function you want to kind of minimize with respect to kind of beta, right? So that means that you start with any random point, okay, and you update it in a way. So let's say your beta I plus 1 is equal to beta I minus del L del beta, where L is this function, right? Which is, if you do that, so let's say exactly it will come like this, right? So yeah, right. So let's say yeah. So if let's say you start from here and you want to come here, right? This is what you want to kind of come here, because here you have the kind of minimum this thing, because del L del beta would be 0 here, right? So, but your idea is like if you start from here and then your del L del beta, let's say would be, and you start from here and this is your actual point where you want to come. So you start here. So your del L del beta would be positive. That means your beta I plus would be, so it will move like in the left direction. And similarly, here your del L del beta would be negative. That means if you start from here, it will be pushed to kind of this direction. So the movement is happening in this way. Yeah. Right. So let's say if you see this function, this is, let's say, your loss function. It is primarily if you remember, the function is of, some square function, right? If you see this is a square function, right? yi minus beta transpose xi square. So if you take a square function here, this is square, and let's say your learning rate and all will come there, because learning rate is basically your beta I plus 1 is equal to beta I minus alpha del L del beta. So the alpha, normally you take a less value, because if you take too high, then it might diverge. The idea is that you need to converge this, right? So if you do this, and 1 second. Yes. let's say straight points. The starting point, let's say I give it here. 0.25. That is not happening. I'm sorry, I'm not able to show this here. Okay, fine. Now it is happening. So as you can see, let's say 8 or 7. Okay, so you start from here arbitrarily, and you see that so that for each this thing it is coming down, right? Yep. Right. Now let's say because now let's say if you want to do it from the other side of it, so you start with -7. So right. Now if you increase it to very high value, let's say 3.25, and then what might happen is it will diverge. You cannot see it here. Okay. So it says it's completely diverged outside. Let me do it 1.25 if that helps. See, yeah, it is not converging, right? Diverged, right? Okay, so this is the basic idea of the algorithms of how kind of we do in the machine learning, right? So regression is a very kind of good starting point for any machine learning discussion, because it starts from there. Now coming back to our this slide. So now similarly, we can have so this was the linear regression. Now we can have the same kind of broadly the same setup for let's say classification problem, and where we try to kind of model if y is equal to 1 or y is equal to 0. So this is what y is equal to 1 given x, and of course the theta is the parameters, right? And so basically why we try to kind of say that yi is equal to 1 if theta transpose xi is greater or equals to 0 or is equal to 0 otherwise, right? Where g of theta transpose xi, theta transpose x is equal to 1 by 1 plus e to the power minus theta tx. This is kind of this is basically your this function, right? 1 by 1 plus e to the power minus z function. So this is the phi z function, right? So that's exactly what it is, right? If you see that if z is 0, then this is half. If g is greater than 0, then this becomes kind of slightly, and if g is infinite, so that becomes 1. So from 0 to 1, it is from 0.5 to 1. So from 0 to infinite value of z, it is 0.5 to 1, and from 0 to minus infinite, it is 0.5 to 0, right? So that's what, if it is greater than kind of this theta transpose tx I, which is basically this side, if it is greater than 0, then or g of theta transpose tx that is greater than 0.5, so then we say that it is belongs to class 1, otherwise 0, right? Then everything is pretty much similar, right? Kind of same as the kind of linear regression and all. We have another way of another algorithm, which is support vector matching. And support matching has been kind of there for a very long time. It's one of the kind of very beautiful algorithm, work beautifully for noisy data, because it does not require you to have the sorry require you to have it kind of for all the data points, right? It just requires the support vector points. But the idea is, saying for the classification problem. So let's say there are two classes. There kind of, you can see the red dots and the blue dots. So these are, let's say, these are defined to classes, and let's say you have this decision boundary, which is W transpose T x plus B. This is the decision boundary. Now, if your one class belongs to some other one side, and then that will be, let's say, positive. So the sign of W transpose T x plus B, if it is positive, then let's say it belongs to class blue. And let's say W transpose T x plus B is less than 0, then we'll say it belongs to class red. Right? Now, now our idea is like kind of there will be certain kind of if I and this is called the margin. Now I want to kind of maximize this margin, right? So let's say, and this becomes my support vector. Let's say the kind of lines which are parallel to the decision boundaries, right? Parallel to the decision boundaries, and kind of made by kind of one classes. So this is one support vector, this is another support vector. So these are the support vectors, and we want to maximize this value. That's all, right? So I mean, as you can see here, so W transpose X. So let's say if you see this is X1 and X2. Now, if you see the W transpose T X2 plus B is equal to 1, where X2 is equal to X1 plus lambda W, right? By definition, this will come because it's a line which is perpendicular to this, right? So X2, if X2 and X1 are kind of perpendicular to this, so that means X2 plus X would be X1 plus lambda W. And then W transpose T X1 plus lambda will replace this. And so you can easily see that lambda would becomes 2 by W transpose T W. That means 2 by W square. Now, if we want to maximize this, that means you want to minimize this, because you want to maximize this W. That means you want to minimize this and subject it to yi into W transpose T xi plus B greater or equals to 1 always, because so then you don't have any misclassification, right? Because yi would be 1 if W transpose T xi plus B is positive. Yi will be minus 1 if W transpose T xi plus B is equal to negative, right? That is the setup, right? W transpose T xi plus B positive, that means yi is equal to 1. That means yi into W transpose T xi plus B would be always positive for both the cases, right? If I don't have any kind of classification. That means you have to minimize this and be subjected to this for all data points xi. Okay. So that's the support vector machine. One very interesting kind of feature of support vector machine is that one is like soft margin, of course, because what is this soft margin is that if we allow some error to happen. Okay. So let's say if we allow some error to happen, so that sometimes we kind of give us kind of a soft margin, which is if I kind of, which is basically epsilon I here, right? So yeah. So then we reduce it slightly. So we say that yi is W transpose xi plus B is greater or equal to 1 minus epsilon. Earlier it was just 1. Now we are saying, okay, 1 minus epsilon, but epsilon I greater than 0. Another interesting feature what we have here is this one. It's a nonlinear decision boundary. So let's say, as you can see in the left side, this is a nonlinear decision boundary, right? This decision boundary is not linear, right? But as you have seen the math, it is primarily for all the linear, this thing, right? Linear separation, right? Now, the idea is, can I take it to some other dimension or some other transformation where this kind of nonlinear boundary would become a linear boundary, right? So the idea is, of course, I'll minimize these W transpose T, W transpose W by 2 plus C, of course, summation of epsilon I, that's fine. But subjected to yi into W transpose phi xi. Phi xi is a kind of where I'm transforming, right? Plus B. So this is where I am kind of transforming, right? So in the transformation, of course, there is some transformation using, let's say, function phi. In that dimension, this will become linearly separable, right? So this is kind of, I just show the example, then it will be slightly easy. Yeah. So let's say, yeah. So let's say this is, now as you can see, this is non-linearly separable, right? You can see the red and then there are blue, and the separation is using this white kind of line that you can see here, right? Now this is very non-linear kind of inseparability, and support vector machine requires a linear separability, right? So then the idea is, and how do you do that? So if you transfer it to some other plane, as you can see here, so you project these points to some other plane, right? 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 And now you can see that you can linearly separate these, right? Right? Clear? That's the whole idea. Okay. So if it is a non-linearity and also project it to some this thing, and the math is kind of very beautiful in handle this, right? So yeah. Right. Okay. Okay. Sorry. Yes. Okay. I'm not getting into this fine. Now the next part is and then similarly you can do also regression where you don't want to maximize it, you basically minimize it, and so that you can. There is something another form of support vector machine which is called support vector regression, which is not a classification problem, which is a regression problem. Where you just want to kind of, you can think about it as another line, but you don't want to separate it. You want to kind of have most of the points and all within certain boundaries. That's the whole idea. But other things and all like this kernel function and all would hold, right? Okay. Now coming to the artificial neural network. Okay. Now in artificial neural network, the idea has actually comes from long back, comes from human kind of intelligence and all, right? Like the way kind of our brain or nervous system is structured, right? As I don't know, some of you might have biology in +2, so might be aware of this. So this is basically one neuron cell, right? And our entire kind of signals and all what it basically transferred through kind of this cell structure. So this is nucleus and all. This is the synapse. Synapse is where the connections happens. This is the signal path. This is called axon, and these are the axon terminals and all. And these things called dendrites. Okay, this is very similar. This is a beautiful picture actually, which basically you can see that. So these are actually the synapse and all, which is coming from the axon of the previous neuron, which is let's say is coming from there. And let's say these are the connections and all, it's getting summations in this body and all. This is the cell body, and then there is some activation functions. And through that activation function, it basically becomes like, so you can see that f of this f of summation of wi(xi) plus b, and that gets kind of to the next neuron. That's the whole idea of artificial neural network, right? And we try to model that every day, kind of in a neural network structure, right? And this is the very basic backbone till today's most advanced deep learning networks which we see. Okay. Now, there are many transfer functions are there. So transfer function is this function, right? So this is very simple, right? You have this is beautiful, simple structure, right? You have signals, which is synapse and all, which is fine. Basically, you can think about it as, so you have many signals, let's say X, and also here you have double transpose TX, and that goes to some kind of an activation function. So it becomes f of double transpose TX. So that activation functions could be many things. It could be a linear, simple linear function also. It could be a sigmoid function, which you have seen earlier. It could be a hyperbolic tan function. The only difference between these is at 0, this becomes tan hyperbolic becomes 0. It could be a ReLU function. We can rectify linear output. That means if x is equal to x, if x greater than 0 or is equal to 0 otherwise. It can be leaky ReLU, which is f x is equal to x, but f x is equal to kind of alpha x if x is less than 0, right? If x is equal to x is fine, same as ReLU. If x is equal to alpha x, or alpha is very small number, and we will see some of these things we'll discuss deep neural networks and the leaky ReLU because it gives you some way to kind of in the negative region and all, in a way to kind of backpropagate and thereby reduce the problem of vanishing gradient. Then you also have exponential ReLU, etc., which we call ELU. Okay. Now this is the gradient descent which I earlier discussed. This is the same here as well. So theta updates rule is basically theta minus alpha del L del theta. Alpha is basically your learning rate. And if you have seen, as you have seen earlier, so if learning rate is very high, it will divide. Learning rate is, so that's the kind of art of machine learning. So you need to kind of tune that. In a sense, like it should not be very high, it should not be very low. If it is very low, then the updates will be very slow. You will get convergence at a kind of very slower rate. And if it is high, very high, then it might diverge. Right. Now the idea is like you have a minimum point which you want to find. This is the global minimum, right? But many of the cases, you will figure it out that it will I mean, and actual deep learning problems, you will see that it is very difficult to find. It's not very difficult; it's basically impossible. There is no theoretical backup that will ensure that you reach the global minima. But what we try to get is kind of a local minima, and whether that is good enough. That's the whole idea. Okay. Yeah. So the gradient descent algorithm, as you know, so this is simple. So you have this loss function, which is some favorable loss function. You have seen earlier a loss function, which is yi minus x transpose t. I mean x transpose theta whole square. That's one of the loss functions for regression and all. There are many other loss functions and all, which we'll see for classification. There are some loss functions, cross entropy loss, etc., etc. But whatever the loss function is, you try to kind of apply the gradient descent rule. Basically, you do a nabla operator or grad operator for each of theta. So grad of L theta, and then you basically apply this here. So your this would be like theta updates theta I plus 1 is equal to theta I minus alpha grad of theta L theta, right? Now, sometimes we are not able to do the entire batch, because if you see this, because this will be over the entire I is equal to 1 to m, right? That's the loss function, because you have to sum the loss for the entire all the data points. Now you might have billions of data points. Now in that case, for each step you cannot compute this, right? This is going to be very, very computationally expensive. Now what you do sometimes, there is something called stochastic gradient descent. That means you take a mini batch, which is here, right? Which is basically same as this, but you are saying that I'm not taking m enter, I just take an m hash. Well, m hash is statistically kind of with a random sample set from the entire data set. So that's what this stochasticity coming. That's what it is, stochastic. And we can show that that it will also, like, G is an unbiased estimator of this one. This is very, very important, right? So this is actually converged to, so expectation of G is actually this grad of L theta. So though I take a mini batch, which is basically, of course, a smaller size of the entire actual data set, but this is actually a very this is unbiased estimator of the you can show that of the unbiased estimator of the actual grad function, right? So yeah. Okay, so that's so, and this should basically kind of, cost of training with SGD is kind of order of 1 as a function of m. Yeah. So this cost will significantly get reduced, right? Okay. Now, the next part is that how do you backpropagate, right? How do you update these kind of to the basically? So let's say this is the output layer, right? So where you have, let's say this is your input. So your at hidden layer, it will be like, let's say my activation function is sigma. So this is sigma of xw1 plus b1. And here my output is, let's say this is y, so this is h of w2 plus b2, where sigma x is this, of course, is my sigma function, and my loss is this, right? Y minus yt is the whitelist target whole square, right? Y, yeah. Now, the idea of, I mean, I'm not getting into the entire backpropagation. The idea is this actually. So if you see of these, so you need del L, so you need to find these W2, W1 and all, right? W2, W1, B1, B2 and everything, right? What you do is you just apply a basic simple chain rule, right? Del L del W2 is equal to del L del Y by del Y del W2, right? Del L del Y is del Y del Z Z2 and del Z2 del W2, right? As you can see here, right? And similarly, you can get the del L del W1 also by applying the chain rule, right? Del L del W1, which is here, is del L del Y and del Y del W1, and del L del Y del Z2, del Z2 del W1, and this one is del Z2 by del H, and del H by del W1, and del H by, then you again break these del H by del Z1 and del Z1 by del H. So basically, from here, you have to go to here, right? Through the kind of use of a chain rule. And that's all it is, nothing much. Right? It sounds very simple, but when Hinton wrote it, it was not very simple. So you might be knowing Geoffrey Hinton, who got Nobel last year in physics actually, but for his contribution in artificial neural networks. So he was one of the one of the prominent researcher, and he actually proposed this backpropagation algorithm long back. I think 82, yeah, 82, yeah, I think so. Might be, yeah, around that time, yes. This is old algorithm in that way. And this is still a backbone of the most advanced deep learning algorithm that you see. Okay, there's the backpropagation algorithm. Okay. We do sometimes call something called regularization. This is basically to make sure that you do not overfit the parameters. That means you do not get unnecessary kind of weights. The weights should not be very high, so that basically what will happen is then it will work might be very well in the training data set, but when you deploy it and when you have the data sheet which is not exactly slightly defined data set, or your test data set is different than the training data set, then it might not work. So what you
sir,
try?
hello, sorry to interrupt you, sir. Just I have a question.
Yes.
If you have some numerical values, so how in previous slide, how these derivatives are computed with respect to numerical values?
Which one? This one?
Yes. That DL D omega
Yes.
W1.
Yes. These are all numerical values, right? So you will have to have numerical values. These are actually at that point, right? So what you have a function and all which you know, because the function you will be knowing because of the activation functions and all you have designed it, right? So your actual function is somewhere like this, right? So these are your actual function, right? This is sigma and all you know, right? Because you have designed it. Now the idea is like you at particular at each point and all. So let's say I come back here. So let's say this is your update rule, right? So your theta I plus 1 is equal to, let's say, theta I minus alpha, let's say g, which is that function. Now how you do it is basically for any like a differentiation and all, you just do a dy dx at, let's say, x is equal to xi. That's what it is, right?
So sir, basically,
Yes.
we have predefined functions. So
Yes.
after we can compute derivative by ourselves,
Yes.
then we have some kind of algebraic expression, and then we put
Yes.
those values there. We
Yes.
don't need to do this derivative, is it?
Yes, no, you need to do this in a numerical way. It has to be done in a computer and all. But if you want to do it in a manual, like in an analytical way, you can do it for small architecture and all. Of course, you can do it. Yes, exactly as you are correctly saying. So you have this
Okay, for large one, I need to do derivative numerically.
Exactly, because you'll be lost. Like I'm talking about, let's say I'm just showing it 1 or 2 layers, but actually it will be exploded, right? You'll have billions of layers, right? So, or billions of parameters. Then it's not possible. And let's say even if it's, let's say, small these things and all, but if you have a very kind of deep architecture, let's say you have thousands of layers, then also it will explode, right? It is very difficult for you to kind of do it analytically. But the idea is, as you have correctly said, so basically you can go ahead and do this as a kind of just write a functional expression and then do a differentiation, and then at each point, that's exactly what is done in computation actually. That's exactly what we do in the computation, right? But what you do is there is some tricks and also while you're doing it and all, you store these values, okay, and then you just multiply. so that you get this because of the chain rule, right? So you do these values as you go along, and then you store it. I'm talking about how does it done in actually at the time of implementation of the algorithm, and then you store it, and then you quickly multiply it. That's the whole idea, and then you update it, right? So one thing that I just want to mention here, because we are discussing this. So you update all the parameters, then only you do the next pass, because you are doing it multiple pass, right? Till it converts, right? Because you have to come back here, right? So till it converts, you have to do it multiple passes, right? Like as you have shown it earlier, right? This one second. Right. So this one, or I can see this one, right? So you are doing it in multiple passes, right? So because you need to have this convergence and all, so you're doing it in multiple passes. The only thing is, once all the weights are updated, then only you go for the next pass. That's the whole idea. Here it is basically a very simple example. You have only one, so that's fine. That's easy. These are toy examples, all. But yes, right? Yeah, clear.
Yes, sir. Thank you.
Yes.
Thank you.
Okay. Yeah. Okay. Now, yeah. So regularization as here. So regularization is basically to ensure that you don't have a overfitting, just to avoid the overfitting problem, right? So basically, you add some kind of some regularization this thing, so that the idea is here. So this is your loss function, let's say. So you just add another this thing, which is this thing, and if you want to minimize this, so you have this thing, this alpha, sigma, theta, and the idea is like if you want to minimize this, so this also like you have to minimize. So basically, it increases a bit. That's the whole idea, nothing much. Okay. There's another way of regularization, which is called early stopping. So you don't train for the whole thing. So this is your training, and this is your validation. So green is your validation loss, blue is the training loss. So there you can see the validation loss is not moving further, right, after some point. So as you can see, so let's stop here. So your training loss, you don't want to go further till this point, to 200 epoch. Around 50 epoch and all, you can stop. That's absolutely fine, right? Because your validation loss is nowhere going improved from 50 to 200. So there is no advantage of training till 200 epoch, right? That's also another way of regularization. Weight initialization, as you know, this is another problem. Like where to initialize the weights, right? Now coming back to here, so weight initialization is this, right? So where I will do the starting point, I'll do it here, I'll do it here, right? Let's say and these things would change, right? If I do it from -5, if I do it, let's say, so these things might change, and how do they converge? Where do they converge? All those things might change. So there are a lot of kind of school of thought in how do you initialize. One way of initialize, of course, you initialize everything as 0. That does not work very well. Random initialization is one thing which might work. What we kind of nowadays, which you do either Xavier or Hay initialization. So this is the way you kind of initialize. It basically is a Gaussian distribution. Both are where sigma is 0. Of course, it's basically these are standard Gaussian, 0 and sigma, and then sigma is, here it is like 1 by root over n minus 1 with number of neurons at the previous layer. That's all, right? And same here on the Hay, but Hay it gives just a 2 and all. There's some advantages here and there. So if you use TensorFlow or PyTorch, you will see one of these initialization. Now, just to kind of taking a before we go to the next section. Now we have observed one thing very interesting, right? So if your data is increasing and all, and these are your traditional machine learning. So your traditional machine learning means the kind of regression or let's say support vector machines, etc. So that actually after initially it will perform very well. as you can see from the small neural network and compared to the large neural network. So that's what I was saying, that for support vector machines and all, for the small noisy data, it work beautiful. But as your data increases, your performance of the kind of small neural traditional machine learning algorithms might not work very well. It's basically slowly getting stagnant. Small neural network will do slightly better, but still, I mean, up to some time after that, also it will start getting saturated. Whereas the large neural network, because for the small number of data and all, it will not work very well, because it requires large number of data points just to kind of for the optimization to converge. But once it has that sufficient number, it outperforms both the small network as well as the traditional machine learning. So that means that with the data, as the data increases, the kind of this performance of the large neural networks kind of increases kind of exponentially, right? So that's compared to the other small neural network and traditional level algorithms. So that's one of the interesting kind of observation, and that's one of our motivation also to kind of study deep neural network.
Just a question, sir.
Yes.
Here data for if we have a same problem, and if we choose small neural network, then we need smaller number of data set, and for large neural network, same problem.
Yes.
We need a larger number of data set to get sufficient result. Is it?
I'll put it in other ways. So if you have a small data set, you don't require large neural network. You don't require deep neural network. Okay. If you let's say if your data set is small and noisy and all, you might be very well with let's say support vector machines or regression models and all, right? Now, if your data is very large, so that means, and your problem also is significantly complicated, you go for deep neural network. I'll come to that in the next section, and we'll see why. I mean, the idea is you see the data, you see the problem, and then you choose the network, not otherwise. Understood? No. You choose the solution for the problem, don't choose the solution first. So if you have a particular problem and all, let's say I want to understand the relationship between the variables and all, and you have a small set of variables, then maybe regression is the best one. You understand what I'm saying, right? Right. Or yes, right. But let's say you have many kind of your data dimensions are very, very high. Your environment kind of significantly high. Like think about the image 1024 plus 1024. That means 2 to the power 20. It's a huge dimension image, right? And you want to kind of do some classifications and all, and that becomes a kind of very cumbersome problem. I mean, practically kind of impossible to handle by the small networks or other traditional ML algorithms. Then deep neural networks is the only one to go with. There is another reason also why you go with deep neural networks, which I'll discuss later. Okay, I'll take a 5 minutes pause, and then maybe you will start at 6:15. Okay. Okay, I'm asking. Is that okay?
Yes.
Meanwhile, if anyone has questions and all, please feel free to ask. Shall we start?
Yes, you can start.
Okay. Yeah. So, so this is one of my very favorite quote. Like, because what is the definition of artificial intelligence? So, one definition which I like by none other than John McCarthy is that the science and engineering of making intelligent machines. I think there's a simple one, kind of makes sense, right? Now, all of the things which you discuss and all, AI is a very broad this thing. ML is one kind of subset of AI, and then deep learning is a subset of ML, right? Because AI could be, it's other things as well. So anyway, now as we are discussing, so one big difference of a simple neural net or kind of from the other machine learning algorithm of the deep learning is that, so let's say in a traditional machine learning algorithm, we normally mention that what is the kind of, what are the features, right? Let's say I want to predict house prices. So I know the features. It could be maybe the square feet of the house, maybe the locality, maybe the city. These are the things which primarily helps me to predict the house and all, right? But let's say if I go for an image classification, whether the particular image is is a human, or let's say a tiger, or whatever it is, it's very difficult to understand those features and all. So what deep learning does is, and not only for image, for any other, let's say kind of a song recommendation, or let's say song classification, particularly let's say I have a song, in which genre it belongs to. Is it hard rock? Is it folk? Is it metal? Is it, I don't know, country? Is it Rabindra Sangeet? Whatever it is, right? Now, how does it understand this, right? So it's very difficult to kind of handcraft those features. Now, one of the advantages of deep learning is that, so these features we don't need to handcraft, right? These features are expected would be automatically extracted by the architecture and then fed it to the final classification, etc. Now, as you can see in the deep neural net, that's what very, very important, right? So you have certain convolution layers and all, and talk to whatever is convolution and all, because convolution is one very important part which you need to focus on. So this is the convolution, and then you have a pooling. Now here you basically all the convolution and pooling and all, what you try to do is you extract the features. Now once we have this feature extracted and all, and the final layer, you do these things, you flatten it, and then you feed it to the classification, this thing, and as a whole you get the final output, right? Now as you can see, this convolution becomes very important here, right? Now, what is convolution, right? I'm pretty sure that some of you might be coming from signal processing background and all. So if you, I'm sorry, 1 second. I don't know why it is not playing. It should play also. Sorry. Okay. The idea is like, if you let's say the convolution theorem is like I'm just trying to see. Yeah. So let's say you have, let's say, kind of some operation of the convolution operation also, that's mathematically this is written as like here, as you can see. Okay. And so which is, you can do a kind of a Fourier transform and all, and you can show that this would be kind of your Fourier transform and all. I just want to show this 1 second. Let me see if I have this. Okay. Let me just share these. Okay. Can you see this? Yeah, fine. We just focus on this part. Okay. Yeah. So let's say this is the signal and all, right? And these are all your kind of this thing, your Fourier decomposition, right? I'm assuming that you have some understanding of Fourier decomposition. If you do that, so these are your decomposed Fourier this thing, right? And these are the kind of amplitudes and all, right? and this becomes your Fourier components and all, right? Now coming back to this, it comes from signal processing. That's why I'm kind of spending time here. So if you do this, and so it will be Fourier inverse of this. Okay, and this is very, very interesting, right? Now Fourier, so Fourier inverse of this. So that means if you transfer it to Fourier domain and then you just do multiply, right? And of course there is some constant other which is root over 2 pi, and then you do an inverse, you get the convolution function right here. Right? That's what it is. So you have feature map, which is basically input kernel. So that means basically the Fourier of input into Fourier of kernel. Kernel is that kind of function which you are applying to extract feature, right? And I mean that's as simple as that, right? So that basically it's a Fourier inverse of with some constant, of course, which is over 2 pi, but then you have Fourier of the input and the Fourier of the kernel. Right? This is slightly this. But if you do a Fourier this thing, so you get from this image, you just a Fourier. If you do a Fourier transform, it will just become like this, right? In other words, maybe this would be helpful. So let's say if I have this butterfly, I do a Fourier transform, which becomes this, and let's say I want to have some kernel function, which is basically do a Gaussian blurring here. But that Fourier transform is here. Now I apply to this and this, right? So I'll get kind of some function of this, right? And if I do a Fourier inverse, I get this function. Understood? This is basically the convolution operation here happening, right? Now, again, I repeat here, right? So you have let's say you have a butterfly, or whatever the image is, you transfer it to Fourier, right? That's what I'm doing, right? If you have then you have a kernel function or the filter. That also you do a Fourier transform here, then you do a multiplication, right? And then you do a Fourier inverse, then you get this one, right? This is your convolution.
Sir, is it a pixel by pixel Fourier transform, or how
Here it is. Here it is.
transforming this?
No, you're correct. Here it is, because you can see that this is pixel by pixel, right? Then only I get this. This is black completely. Yes. Yeah.
No,
Right.
no. My question is, we have a 2D image.
Yes.
So how we transform this, by making it flat or by 2D transformation?
By 2D transformation, yes. No, you're correct. 2D transformation, yes. Okay, to flat I'm not coming here. I'll show that later. So it's not there. Right now it's just a kind of it is still very much in the signal processing domain. I'm not getting into the deep neural network. I'm just trying to kind of making my point here is that from where the convolution concept came. That's all. The idea is like it helps me to kind of extract certain features and all, right? Here it's just, of course, it's just doing a blurring and all that. Now I'll show you the actual features and all, right? So let's say I just here, right? So you have this, then you have, so this is a low pass filter. That means, so low pass means, so if you see that, so these are like, this is your, low frequencies is basically in the inside, right? Others are high frequency. Now you have only this, that means a low pass filter. So that means everything else would be, once I multiply it, everything else would be zero. Exactly that has happened, right? So this filter, is basically a low pass filter because by design, right? So everything else is kind of black. So if I multiply it, everything else will be zero. Only the low pass one, only the center one would be would exist, right? So if I do that, so this is my low pass filter, and if I do that, so you can see the image will be blurred. For the high pass filters, the high pass filter basically where the edges and all is basically where the the frequencies will be high, right? And you can see that. So the high pass filter is just otherwise, right? So everything will be white, but only this dot will be black, right? So that means I will pass everything apart from the center part, right? If I do that, then this is my, if I do the inverse compared to this image, then only the edge will be there because there the frequencies are high. Right? That's the whole idea. So if I have these two filters designed, I get the low frequency features, I also get the high frequency features, right? This is the concept which has been applied for the deep neural network. However, the kernel functions and all are slightly defined. It actually happens otherwise. That's all. Okay. This is the great AlexNet and all. So 2012 actually the first time. So there is a competition in ImageNet to understand like how better these classification algorithm, how better these methods are. So before 2012 and all, it was all the efforts and all were to kind of feature engineering and everything, right? Now 2012, one very simple, one interesting thing happened. So um, uh, Alex was a student of Geoffrey Hinton. They prepare and Ilya, of course, who was later with the OpenAI and all, and then started his new this startup now, and of course Hinton. They proposed this architecture, and that basically kind of do the exactly this thing. I mean, I'll show that kind of very simple single architecture. So all this convolution layer and then pooling and then kind of uh, convolution, and then of course you have activation function ReLU and then pooling. All these things is there. After that, you have these things have been flattened, and then you have couple of fully connected layers, 3 fully connected layers, and then that goes to a kind of a softmax function to classify. It's a very simple idea, but the whole idea was this, to extract the features automatically. Okay, and that worked very, very well. It was far better results than the existing algorithm that time. That was the AlexNet, which was one of the first deep neural networks in 2012. Right? It is just 12, 13 years of this entire progression and of the deep neural networks of deep learning, whatever we see nowadays. Right? Also, I should mention here, because we are discussing this, there is one part also, the algorithms and all, like the backpropagations and all were there. But one difficulty that you have faced earlier is to train these things, right? Now, during this time, there is also the parallel development happens in chip, right, where you actually do the computations and all. And NVIDIA very cleverly, they observed that these because these are massive computations and all, but could be parallelized, because broadly the computations are matrix multiplications or addition. And that's why you don't require very powerful logical unit, but a logical unit which can do can handle multiplication and addition should be fine. But it can be massively parallelized, because each layer and all, so all these computations and all at each layer does not depend on each other. So for each layer, it can be parallelized, right? Sorry. So it can be parallelized, right? And then they built something called CUDA, which is basically kind of a library to kind of help in this parallelization. And then of course the other CUDA libraries and everything came, and then of course now the NVIDIA story started. But that also helped to make it possible to run these large algorithms in a very efficient, in a compute efficient way, in a kind of to be able to compute this in a kind of in a expected time. Yeah. So earlier it was not kind of possible, right? So and then of course later other chips also have started coming out, like Intel brought Habana, Intel HPU, GraphCode has its own called IPU, Cerebrus has its own, everyone has its own now. But of course, NVIDIA still enjoys this entire CUDA libraries and all. Right? I just wanted to say that, because that also is the important part, because it's not only the algorithm, also you need the compute machineries to run those algorithms, right? That's the whole idea. Now coming to, now I'll spend some time in just showing you the, okay. Let's say this is a trained network, okay? So let's say you have, let's say you have this input, and you have red, green, and blue channels and all, and these are their respective values. Now, as you can see, this is the convolution of kind of these things are happening, right? This is the way it happens, right? The same kind of filters that get applied for these 3 channels, and then they get summed, right, with some bias and all, right? So this is one feature and all, right? Like similarly, you have these. This is another kernel, right? I mean, this is another kernel which is being operated, right? So as you can see, there are 10 kernels, like 62, 62. So the images are like 62 plus 62, but your this is like you have like 10 kernels, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the first layer of these, right? Then you do a ReLU operation and all. Then so these are the output of the ReLU, right? So this is what is happening, right? Right. So these are all like if you have a this is negative value, right? So that's why you can see that these are all 0, right? Right. Only here you can see some positive value. Yeah. Yeah. So here there is 0.28 and all. So some of those minor positive values only will get transferred, right? That's the whole idea of ReLU, right? Right. After that, you again apply convolution on these, right? So if you see these, right? So yeah, all of these are the convolutions are happening, right? These are the debug layers, right? Right, and then again you do a ReLU and all, and then you do a max pool. Max pool means max 2 plus 2 pool. So whatever is the maximum value, it is basically kind of storing it here, right? If you see of this, so it also helps you to reduce these things. So you have this is 62, 62, this is 60, 60, but the moment you do a max pool, it will become 30, 30, right? So after that, again, you do convolution layer and all. And this is very simple architecture. This is just to kind of, for a toy example, but just want to kind of show. And the same thing happens again for the convolution, again, then ReLU and all, this will go on. And in the last layer and all, this is where you have the final layers and all, right? So if you see here, right? Yeah, so this is your flattened layers, right? All those layers have been, these are your final kind of features which you have. That's what I wanted to kind of have these. So this is your final features which has been extracted. Okay, these are the final features and all which has been extracted. Okay, now let's say how do you do this? You flatten this, all those things and all, right? So this is your number 1690. So these are your final features. Now this is very simple. So you have a fully connected layer of here, and then some mass function, and then that goes to a softmax, and you hit it. And you the most because of the softmax and all, the nature is that this is the highest probability and all. You see the pizza is the highest probability. The pizza is the highest probability. The others are also like for each it will give you some probability and all. The pizza is the highest probability, as you can see. So it will say, okay, this is most probably this is pizza. Clear? This is the way kind of.
Sir, what is our input here? What is our input?
Input is this image. And then three layers.
At the leftmost column, you see you have 3 inputs actually. I don't understand that.
These are for different channels. No, you have RGB. No.
Okay.
So one is for red, one is for green, one is for blue. Yes.
Yes, I got it. Okay.
Right. Yeah, but the idea is like so the difference here is.
So
and
if we do it grayscale, then we need only one channel for this.
Yes, of course, yes. Of course. But whatever channels you do and all, as you can see, you basically sum it up. That's all, and that's all for the file. So this is for this one, right?
I think that it is the satellite data image processing, no DIP, digital image processing of satellite data.
This is not satellite data. This is simple pizza image.
Oh, okay.
Simple pizza image. So whatever you want to do is just not a problem. But
in the same way, we are doing the satellite image also, no?
You can do satellite image as well. You can do any image. You can do medical image and all. Algorithms would be same broadly. You have to train it again and again because your weights and all will be different. Yes. Now the idea here is what I'm trying to say is you have 3 channels and all. That's why you're summing it up. If you come here, from here to here, let's say from here to here, you'll get sum over the 10 channels, right? As you can see here. Right. So the each kernels operates on each of these and then gets summed. That's the idea. Okay, but that's not the idea. The more idea, that's probably the engineering part. The more idea is here that you extract the features. Here these features and all these are the final features. These you extract, and this is the very default features and all. Right, for each layer you are having. I'm sorry. So for let's say for these are the extracted features and all. So that's very important, right? I'll show you the cup image. You'll understand this a bit. These are some of the interesting features of cup, right? You can see that this is the edge actually. If you see this is broadly it is getting the edge, right? So here also, right, you get some round shape and all, right? So these are the features which it is getting extracted automatically, right? So the idea of the deep learning is this. So you don't explicitly say that these are the features. I'm not saying that you look for a circular this thing, you look for this edge and all, because it's very difficult. This is exactly the way we understand also. That's why it is the deep learning is so interesting and it is so inspired. I mean, it's so similar to the way we perceive the world, right? We also perceive in a higher dimension, right? Like we initially, if you see, let's say, we are very good at understanding whether it's a human or non-human. And within human, it's called hierarchical learning, right? Whether it's a man or kind of woman, or it's a child or a kind of adult, right? Or kind of a long hair or white hair or Hispanic or Asian, right? So it's kind of very, very hierarchical learning, right? And we first understand certain features and all which differentiate, let's say, human from others, or let's say a fish from others, right? Then on the particular fish, certain features which will differentiate, let's say, Hilsha from Katla, right? So that's the whole idea, right? You learn those features in a very hierarchical way, and once you learn it and all, you can define, you can identify. Right? Yeah, and then if some of the function does not work properly, some of the kernel does not work properly, then the kind of the perception of the world will be very different. Yeah, that's the idea, right? Okay. Yeah. So you go back. Sorry. This. Okay. Now this is the on the vision. I mean, primarily on the vision side. Now there is another architectures and all, which is from the let's say time series modeling, right? Now here the interesting part is that you have let's say think about a kind of a continuous data is coming, and those data are, let's say, time series data, right? So language in a way is a time series data, right? Because we speak, we read and all, and so there is a sequence of data, right? It always may not be time series, maybe the better way to put it is a sequence modeling, right? There is a sequence is important, right? And let's say it could be an image classification, my apologies. It could be, let's say, a language translation task. So the sequence is important, right? So let's say if I say in Bangla, in like Amar Naam Amritendu, so that will become my name is this. So the sequence becomes very important. Some understanding also is important. Okay. We'll see there are nuisance here as well, because if I say that Amar Naam Amritendu and I say Amritendu Amar Naam, broadly the same thing and all, and that's why transform architecture also will come into the picture. So sometimes it is not also always the sequence also, sometimes it goes otherwise. But some of the data could be very rigid and sequential, right? Let's say, as someone was saying, like continuous data which is coming from the satellite, let's say satellite telemetric data or any telemetric data, any constant observation, monitoring data, right? They're all continuous data and all. Now you want to work with this data and all, you want to extract features and all, and then you apply the deep learning algorithms. So one way of doing it is that called recurrent neural network. This is the why I'm saying recurrent neural network, because of course this is very kind of backbone of time series modeling, primarily sequence data modeling, which is basically kind of go to transformer architecture and all. So let's say you have X, you have from X to Xt plus 1, and these are your outputs, right? So as you can see, so of course output at level T depends on Xt, not only on Xt, also on Xt minus 1, right? So all the previous output also is impacted this. So that's the whole idea, right? So that's what we sometimes call it auto-regressive model also, because this is important, but this also get regressed over its own value in the previous time, right? So here the OT is a function of Xt as well as Xt minus 1. Xt minus 1 is a recursive, right? Xt minus 1 is the function of, OT minus 1 is the function of Xt minus 1, but as well as Xt minus 2, right? That means OT is not only a function of XT, it's also function of XT and XT minus 1 and XT minus 2. Correct? So that's the whole idea. One problem we see here, and I'll not get into the details of it, but it might happen that a very long earlier context, let's say X and all, if the T is very large, then this impact might get lost here. A classic example would be, let's say, if I say, let's say, some example where, let's say, this gender, say, how can I say it? Let's say, let's say Ramchandra was the king and all, and then we go ahead, and then at last there is something called he killed Ravana. Okay. Now, whether it will be he, that depends on Ramchandra was the king, right? Right. So Ramchandra was the king, so it should understand that that's a gender, male, and that's why it would be he. And that might be comment very, very long. And in that entire process, it might get lost. This might get lost and impact and all when you do the back propagation and all, right? So the gradients of these, the weight updates and all, might find that there is not much of importance because this is very earlier, right? It might be happening at X0 or X1, whether this is at X, let's say 100 or X200. So, and in that process, when you do a back propagation as you shown earlier, that kind of gradients and all might be very, very minimal, right? So you cannot really try to back propagate, right? So now for these problems, I mean, so it could be otherwise, right? So let's say, I mean, so you need to understand that, right? Now, or you need to have some mechanism so that architecture remembers that. So there are some recording called long short-term memory and all. This is basically what it does. It's kind of, there is some gate. So what we do is we switch on and switch off the gate in order to, whether we basically use a signal, whether you want to remember it information or not. That's the whole idea. Okay. So Ramchandra was the king. So that information it will remember till that last thing when he said that he killed Ravana. So till that it will remember, right? So that's one way of kind of having this this thing in the LSTM and all. Like we'll see later in the transform architecture, it is done in a more efficient way. Okay, so now this is the classic encoder decoder architecture of LSTM. So you have these, let's say these are the LSTM, these things, these are the different state vectors. And then that goes into this is the encoder and all, and then you start decoder. Let's say it's a classical machine translation problem, right? So let's say you're going from English to French. So you have this, and then this is the encoder, and then you have a decoder, but this is the kind of a state vector which directly goes here, and then it gives the initial output. And then once you start happening, then basically the idea is, so after this, this is exactly similar as this, as you can see. These are the LSTM block, and this is different kind of timestamps, of course. And then you have this decoder block, right? And then you start kind of decoding and all. And for each this thing, it gets concatenated, and then gives the kind of fully kind of current layer, and it gives the final prediction, right? For transformer architecture, this is in a slightly different way. I'm not getting into this this architecture and all, because that will take a lot of this thing. But the whole idea is basically what we try to do is we try to understand how important of each word and all with respect to the other words. Okay, that's the whole idea. Okay, we try to kind of measure a kind of a relative importance of all, and then we fed it for the decoding and all, so that for the entire context and all, and you will always have this 1 million token or the context size and all, the generative modeling and all, which is basically, so understand the entire context in a single shot. Of course, there are multiple attention head and all, but each attention head, what it does is it basically measured for the each word or token how important it is compared to the rest of it. Right? So basically, it finally does a relative importance and all. Right? I'll show you one example that will be exactly similar to this. Okay, and that's all. This is exactly what it is doing. Right? This is the weight and all. Right? So that's what it is does. Right? Mm. Yeah, and you have multiple attention head and all. That's all. Yeah, so you have this feed forward network, this is the encoder block, and then exactly the same as the decoder block there, which you have seen earlier also, broadly the same and all, right? So you have this one, and then you kind of have a feed forward network, which was there here also, right? Right, in the LSTM as well. And then you have a decoder block here, right? That's broadly the transformer architecture. Now I'll pause here and I'll show you one transformer architecture. 1 second. Okay. So data visualization empowers user to visualize. Okay, whatever it is, I do not know, right? So these are the tokens. Okay. So data visualization empower. These are the tokens, right? So this is the tokens and all, right? Now, as you can see, so data visualization. So these are query queue value and all, and this is the attention and all. So if you see here, and as you can see, right? So that's why this is computationally very expensive. These are order of n square because it is doing so this thing, it is actually kind of trying to, and as you can see here, right? Here, if you see, right? So exactly, you can see, right? This is the importance which is getting a rank here, right? 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 This is the attention mask and all, right? 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 Right. So it is basically trying to understand for each of these, of course. These are basically embedded. They're embedded in the latent space and all. And after that, you basically do this kind of self-attention, which is trying to understand for each of these things. And right, so its final space is 768, right? And then this is the output and all, and this is the rest.
Don't get what is this attention part?
Attention parties for each token. So these are the tokens, right? So data visualization empowers users, etc. Now, attention parties, where you try to understand the relative importance of, let's say, this particular token, which is data, compared to the other. Understood, no? Okay. So like whenever we have a, let's say, a long context or any context and all the tokens and all the words are not equally important, correct? Some will get more important, some will get not, right? So what it does, it is self-attention. Of course, there can be cross-attention also. We'll discuss this later. But broadly, what attention does, it tries to kind of understand the relative importance. That's what the attention is. Where you need to give attention. So where you need to give attention, right? So which are the most important this thing on the, so in the data visualization or to predict the next, of course, you will see the visualization is very important here. Because now you have this thing, so there's, as you can see, so now it is predicting the probability of the next token, which is visualizes the highest. Right? Right? So that's what, so now if I generate, this will be visualized. I don't know why it is. 1 second. 1 second. See? Okay. Now, as is a probabilistic model, and that's what each time you will not see the same kind of results, right? Because it's a probabilistic model. So the idea is, of course, most of the time visualization will come. So if you do 100 times, 54.67 times would be visualization. 12 times it will be C. 20 times it will be create and all, because the based on the probability and all, whatever it is there, right? Is it clear, the attention part, what I'm saying?
Just another question.
Yes.
Before attention, we have the key, query, and value. All these things are same. So what
No,
are the
it is-
significance? Because
No. This is same for the self-attention and all, but this might be different. So I'm not getting into that. So, so idea is like basically you get a kind of, for each key query, kind of a key and query pair, you will get a value, right? So it is not exactly same, but in this case, this could be same. But you can think about here, here might be another transformation and all. You can have another kind of a layer here, which could be kind of, which output of that could be Q. Here, let's say you might have another kind of block here, which would be the output, like some transformation block here, with output of that could be query. Here could be some transformation block here, with output that of that would be value. Actually, there will be transformation block here. Yes. But this is very simple, these things and all, so it is all same and all. But for many cases, it will not be same also. There will be transformation blocks actually before for the each key query. Yes.
so after attention, that part, that data visualization, this outputs we are getting. So so what this
Yes.
gives? No, that MLP part. After attention, it is merging with the value.
Yes.
No.
No, then you get a finally
Not that part. I am telling you that we have attention block which takes key and query, and
Yes.
then it merges with the value. So it gives
Yes.
some output. So what
Yes.
we are getting after
So
attention?
this
that
is the
MLP
encoding
part.
part. Understood. This is the encoding part and all. Then again, you have to. So there are a lot of these things which I am not like, as it also mentioned here, because this is very difficult architecture to show. But this is a good attempt that they have tried. Now, so this is an encoding block. Then you, at the end of the day, you also have a decoding block where you want to predict the next word, right? Because your task is to predict the next word. Correct? No. So that's what it is trying to predict the next word, which are from this. So this is the entire vocabulary what you have, right? And from that, it is kind of giving you these percentages and all. That's the whole idea. The temperature and all is basically if you increase it, so it will change a bit. In the sense, so it will be sorry, it will have more flexibility, etc., etc. That's all. Yeah. So it can have many tasks actually, but at least what I'm showing you is the kind of from the prediction of the next token. But most of the cases, it is some prediction, some way or the other. That is true. If you want to do a sentiment analysis, also that's also a prediction. If you want to predict what sentiment it is, or you want to kind of translate, you also want to predict, but from a different language dictionary. Right? So broadly, the task is predicting the next token. And there's the same for the very advanced, let's say ChatGPT and all, whatever you use. Broadly, the task is to predict the next token. And based on the next token, you will predict the next one. So you might see the entire chunk is coming together, but it is actually predicting one by one. Yes. Does it answer to some extent?
Yes. Thank you.
No. I know I need a kind of complete class for this. It is also true. I can kind of compact everything in a 3-hour session is its own challenges. Sorry, where I was. Okay.
Sir, just I have a query that any weightage factor is behind it work? Is there any weight?
Sorry, come again.
Weightage factor is behind this
You
problem?
want this, no, you want that's exactly. So the weightage factor, you want the weights or the relative importance in this case, or the relative importance means which is basically expressed in terms of attention. You want that to be learned by the architecture. You don't want to say anything. You want it to be learned. Yes.
Okay. Thank you.
Yes. So that's exactly what it is. So you want to learn the weights or relative importance, but you want it to be learned, but you do not predict that. You do not, kind of give any directions.
Okay. Okay.
Sorry, I'm not very do a little bit. Mhm. Why did I keep it the next thing? Sorry. Huh. Okay. Okay. Now the next part is is on the deep generative models, which is the other part of it, right? So we have seen image, we have seen sequence modeling, we have seen convolution network, we have seen recurrent neural network, we have seen transform architecture. Of course, we have seen earlier LSTM. Now we'll see the deep generative models, right? So the problem of the deep generative models is to understand the underlying distribution and then kind of predict from that, right? So there are two parts of it, right? One is to kind of understand the underlying distribution, estimate the underlying distribution, and then kind of sample from that. So that understanding is one part and the sampling is the generation part. That's where the generative models comes. Right? Now, this is the classical way of doing it and all is called Gaussian mixture model. So basically you assume that any underlying distribution could be expressed in terms of Gaussian mixtures of kind of n Gaussian distribution and all. So that's the kind of just a second. Let's take this call. Sorry. I'm sorry. I just muted it. Yes. So and you can express in the Gaussian mixture form and all, and then you can have this form, right? It will be like sum of this kind of this thing where it's like sum of pi I and Gaussian of this with some mu I and of course because it's a multivariate Gaussian to some covariance matrix, right? Now, and of course, conclude like the sum of this pi I is equal to 1 to g would be 1, right? 1 second, huh? Just give me a minute. Someone has come. I just need to open the door. Just a second, huh? Please. Okay. Now, if you do it further and all, so we can also show like the earlier we have shown that MLE and all maximum likelihood estimator. Very similar way we can show that the same way it will have because we will have actual distribution and you will have an f theta y because you have parameterized it, and you can show that you like kind of this will be boils down to minimize the KL divergence. Okay, that's the math part of it. That's a classical way of doing it, but we have seen that this is very difficult to do it in practical sense and all because I mean you do not know this how many pi you will take. The actual kind of distribution could be much more complex than you think of and all, right? So whether it works beautifully in theory and coming from the statistical learning theory and all is great and gives a very strong kind of background, but most of the times it's also very kind of it's very difficult to achieve. Now, and that's one of the reasons that we have this neural network, which is primarily kind of a function approximator. If you think about neural network, is there are a lot of theory called universal approximation theory, etc., which basically confirms that any kind of functions and all, if it is, I mean, even it is bounded or if it is unbounded, so you can model it with a more than if it is a single layer, then it could be bounded, or if it is unbounded also, then you can kind of more than one layer and only sufficient to model a any arbitrary function to kind of any arbitrary level of um, error tolerance, right? So that's one of the strongest backbone of neural network. So point here is the neural network could work as is actually a function approximator. So yeah, so that's what the whole idea is. So you parameterize like this f theta y using deep neural network. That's the whole idea, right? Okay, now this is, I'm not getting into this, so this is fine. There's a lot of math here actually in their model, but I'll just try to avoid the math here. The idea on the variation autoencoder is so the idea of here is like you have let's say you have an autoencoding space and you have a decoder. So you have an encoder and you have a decoder. So you have an encoder in the lattice space and then you have a decoder. Now what happens is that you have a reconstruction error and you have tried to minimize that. So that's the whole idea, that how can you you have a generative model, right? So you have certain, let's say certain inputs, and you encode it to some latent space, and then from the latent space you decode it. Now the idea is when you decode it, you generate it, but then and you try to reduce this error of the what you have decoded to, like this, and what you initially had. So that's the error, right? That's reconstruction error, right? And then you try to reduce it, right? And that's to try to minimize it, right? That's the whole idea. Now, in this process, what happens is that it does not, it will work beautifully in the generation phase, because generation phase you don't have any encoder, you just have a decoder, and you basically take any data and all from the latent space, and then you should be able to generate it after the training is completed. But what happens is that if you have a data point which it is not part of the training, then it does not know, where it actually should decode, and it's slightly lost in that kind of latent space. And that might I know that's not actually the expected behavior, right? So what we do is, so this is the whole idea, right? This is the actual autoencoder. So you have an input image and you have an encoder, and this is the latent vector, and then you decode it, right? And this is your predicted image, right? And then you try to reduce this difference between x and x hat, right? But here you do not give any variations and all, right? What you do in a variation autoencoder is you actually try to give certain level of flexibility here by introducing here a variance and all, where you see that your z is coming from also certain distribution of mu and sigma. That means, so this is your simple latent space, and then you do exactly the same thing, but you just introduce this. So your z becomes mu plus sigma epsilon, right? Which is this one, right? So this becomes your g space now, right? Earlier it was like a very fixed space, and all. Now it is basically a distribution space. So that means in order it learns this distribution and all, and you can take any sample from this distribution and it should be able to generate. That's the whole idea of variation autoencoder. One problem we see in the variation autoencoder is that you have two these things here. Okay, one is this error is fine, but so what happens here is how do I put it here? So one is of course this error. So of course you try to reconstruction from the z. So I'm sorry. You try to get to here from z, which is this error, which is fine. But you also it's basically z x given and pz, right? So that means you can define this internal distribution what it should be. You can say that okay, this is a Gaussian distribution. This is a kind of a distribution when there is no covariance. That means all the covariance metrics should be 0. Only the diagonal element should be there. So that helps in to tackle some of the problems, which you say the entanglement and all. So what happens is, and I'll show you some example. And one second, please. Sorry, I have a 3-year-old. So the idea is you so you reconstruct it, but at the same time, you also try to kind of have, you want to the Z to follow certain distribution. Let's say you define that, let's say some Gaussian distribution or whatever it is. The advantage of it, so the advantage of it is if it let's say sometimes you'll see if a generated image, if you want to modify one attribute, let's say hair color, you see maybe the facial expression also changes. This is we know it, we call it as entanglement, but this happens because if there are two, let's say, attributes, one is, let's say, hair color, one is, let's say, facial expression, there will be some relation between these two. If there are some relation between these two, and but you can modify this, like you can say, you can have a variation autoencoder mentioning that, okay, I want all the kind of all the attributes or all the dimension in the latent space would be completely independent to each other, which is great. So you can do that. You can specify that, okay, you find this is what you will achieve. So you want to do that, but at the same time, this might get a little bit of sacrifice because this is kind of a trade-off, as you can see here. Right? So if you want to minimize this, because at the end of the day you want to argue max of this and you want to maximize this. So it's basically kind of some trade-off happens. So sometimes you can do that, but your reconstruction error might get affected. So you might get not exactly the very sharp images, etc. I'll come to diffusion later, but before I come to diffusion, I'll go to the GAN architecture here. Sorry. Oh, I do not know. I do not have a GAN. Do I have a GAN? No, I think all I have is a. Okay. I just quickly show you another way of doing this. Is called generative adversarial network, which is a slightly different way. What happens is you have a generator. I'll show you the demonstration now. So one is basically you have generator. So you basically generate completely from noise. Okay. And then you have some, so generator actually kind of tries to generate the images, and you have a differentiator. Okay, which is discriminator here, and you have a real image and a generated image, and you try to understand if the generated image is different from the real image, right? So the discriminator job is to find whether this is same as the generated image, right? If it fails, so then the generated image, this is complete actually training. So the idea is the generated image job is to fool the discriminator, to generate in such a way the discriminator cannot differentiate between the generated image as well as from the actual image, and the discriminator job is to differentiate between the generated image and the actual image. So so there's a kind of a min-max game what works here, right? So as you can see, let's say this is the data, right? And let's say if I start the training here, yeah. As you can see, right now it is generating purely from noise, right? So it should generate somehow like this, right? Right. So as you can see, there is discriminator loss and the generator loss. It exactly should come like this, right? One should, yeah. Yes. Beautiful. Yeah. Right. Right. As you can see, like both are like broadly like both will converge. Yeah. Now the training is almost converged here actually. So you can stop that and then you can just generate from the sample. So that's the whole idea. It has broadly captured the distribution, right? Understand, right? What I'm trying to say, right? This is the generated one, right? The red color one here. This is the generated one, right? This is the real one, right? So it should almost get the same distribution, but it's kind of, it's okay. This is also serve the purpose, right? If you have these, So GAN was around 20, it was, first paper came in 2014, and 2018, 2019, it was very, very popular. Yeah. Almost it has captured it. I'll show you some of the early work, what we did at, so I had a startup earlier called NeuroPixel.ai Labs. We used to work in the intersection of computer vision, deep neural models, and fashion e-commerce. So very early, like 2021, 2020, 2021, that time, we did some work in deep generative models, of course, using the GAN architecture, because sometimes there's NVIDIA Stylian paper and all came out. I just show you some of the very early work if I have. Just a second. One second, let me just see if I have, so that I'll just show you. Maybe this one. Yes. So if you can see, yeah. So these are all the images that you are seeing. They are getting generated. These are using they're built on top of Stylian architecture those days, right? They are, and you can you can smoothly transitions and all these things, right? These are primarily built on GAN architecture. I just show some of other work so that. Yeah. So here you can see the attribute modification. So you can see that so these are both of them are generated, and as you can see, you can change the hair color, you can change the facial expression, right? And very minute facial expression here. As you can see here, yeah. Right. And as well as, of course, you can morphing. So the hair is generated separately, body is generated separately, but you still can morph it in the latent space, right? So yeah, so that's those are the earlier GAN works, some of the GAN works. Okay, now coming to the diffusion where we were. Okay, now coming back to this, and I'm not getting to this much of math. I'll just come to the point here. The idea of the diffusion model is you have an image and you kind of add some level of noise, let's say, and you get into the complete noise, right? Now, if you get into the complete noise and if you try to come back from the complete noise, right? So basically you start you estimate the noise and you remove the noise. And then if you do the reverse process, then you get the generated image, right? That's the whole idea of the diffusion. So this process is the diffusion. This is the back process from image to noise is the diffusion. From the noise to image also is a diffusion, the reverse diffusion process. So that's broadly a diffusion process again, right? So that's the whole idea. And we do certain thing called a embedding along with the image and the text associated, right? So these pairs and all are embedded in the latent space. And when you generate, you try to you give a text guided. If you cannot give a text, also it will generate something. But if you give a text, then you start the generating process from kind of which is the nearby image and all, which is the closely kind of associated with that particular text, from that, so that you have a similarity in this, right? So that's the whole idea. I'll show you a kind of a similar demonstration of visual demonstration of this as well, diffusion. Yes. So let's say this is the text which we are giving, right? A cute and adorable bunny. I can give some other. Let's say a vibrant Renaissance portrait of an energetic noble woman holding an iPhone. Okay. So that's the text generated representation generator, right? So you basically, this is your text encoder and all, and this is some kind of, in some latent space and all, it is getting kind of embedded. And you always remember one thing, we do this entire diffusion process and all in the latent space. So which is significantly, so you have an image space which is, let's say, 1024 plus 1024, that means 2 to the power 20 image space. But your latent space will be some very kind of completely smaller, like 768 and all. So you do the entire diffusion process in the latent space. And the final generated image and all, again you do a decoder. Normally you take a VAE decoder to get the final image output, right? So this is the image representation layer. If you see the image representation layer and all, so this is exactly what is happening, right? So yeah, so you have a guided image generation here, right? So then you have a noise, right? And then you basically predict the noise. You remove the noise, right? You remove the noise and then you do again the same process, right? So again, using the unit and all, you predict the noise. And then once you predict the noise, you remove the noise. Then you take that, and then you will continuously do that, right? That's what it is you are doing, right? And you are basically generating this from this text, right? Now you can reduce the guidance scale and all. If it is like 20 and all, it will be, if you reduce it, and you can see your guidance scale, if you reduce, that means it basically kind of generate, may not adhere completely to the what you have mentioned, right? So because what happens is we basically have two paths. One is from, let's say, 0, so there is no this thing, and one is of course with the kind of embedding space that you have specified for the text, and then it's kind of do a kind of in between and all based on your guiding scale. Whatever. Just a second, man. Okay, so this is broadly how the diffusion works. This is same for like nowadays. Of course, there are certain other changes are happening. You will see more of multimodal. So the text and image would be kind of have a joint embedding and all. You must be heard of the architectures like JPA, etc. It is primarily kind of work on these, right? Yes. Let's take a pause here. That's the diffusion broadly. Yes. How does it work? The broad architecture is like this. So you have a kind of, this is your actual space and all. This is the diffusion space, as I mentioned. So you have actual, let's say, pixel space and all in the image. And then, of course, you have a latent space where you have the diffusion process. This is like maybe 1024 plus 1024. This is 768 encoded. After that, you do the diffusion process. And then this is the reverse diffusion process. Now, you can modify this by many ways. You can condition these by semantic map, text, images, etc., etc. And that also goes, and then with that conditional this thing and all, it basically now start generating the kind of basically doing the denoising part, right? So that denoising goes on, right? And then as you have seen an earlier demonstration, so each step the denoising goes on, and then again it comes back, it removes the noise again. Like this process will go on till the time it finally achieve. Let's say you do it for 50 steps and all, and then the denoised image came, and then you do a decoder and get back to the um, image space, right? That's the idea. This is one of the latest work what we did at NeuroPixel when I was associated. Was on the it's primarily based on the diffusion architecture. So if you want to I just show you this. So you have just an image of let's say garment. You generate the entire person. You generate the entire background. Then also you can kind of uh, create a little bit of small video from that, right? So everything else, apart from this image of the first garment, everything else is generated, right? That's the strength of the diffusion stack. Right? Which you see nowadays as the kind of deepfake and all is primarily the same algorithm. Right? Okay. I just take kind of just 2-3 minutes before I kind of wrap it. So there is something called reinforcement learning also, which is also very prominent even in basically in training, teaching making the large language model to learn, etc. It's primarily what you do is basically you have an kind of agent which is you have certain policy and it interacts with the environment. So you must be seeing it's very prominent in like robotics and all, but it is also you must be knowing the DeepSeek and all. They also implemented this in terms of while training their model. The idea is like you don't explicitly kind of do it in a supervised way. You don't say what is the right step and all. You just allow it to interact with the environment, and you either you observe it, and either you reward positively or negatively, or maybe basically reward or punish based on that, and expect that kind of agent to learn. Right? That's the whole idea. This is, of course, the agentic workflow because there's a lot of AI agentic workflow. I mean, you must be aware. You must have seen the cloth code and all. I'm very sure most of you are using some level of coding assistance. There's primarily some level of agentic workflow and all, right? So as you see that kind of as a task complexity, so this will best way it will work is basically for the kind of simple to moderate complex task and all. So kind of the automation using the AI agentic workflow would be achieved. However, for the most critical decision making problem and all, it will be kind of human in the loop. Right now, you think about it, right? So you have the standalone LLM power agent, right? Now you have some LLM agents like one agent A and another agent N plus one, which is kind of having kind of certain information sharing. Then you have standard LLM power with some kind of access to tools, right? And then let's say you can between the agents you can share the information. You have access to tools and all. And if that is the case, then you can also kind of have certain level of negotiation. I'll give you an example. This is something abstract. Let's say you have in an organization you have two verticals. Let's say one is function, one is finance, one is let's say HR, right? So let's say now HR has its access. HR is trained on there's an LLM, but it broadly kind of trained on all the documentation, all these things, whatever is available, all the knowledge base which is available to the HR function. And let's say another one which is on the finance is also trained on all the documents, all the knowledge base available for the finance. And let's say there are let's say a new person joins, so that's a task. So the HR agent should be able to handle it most of the cases. That HR agent might have access to certain database where it updates certain kind of tables and all with the employee details, etc. However, HR agent also needs to contact the finance agent because his salary and other compensation, other things also need to be mapped, need to be updated in the finance database and all, right? That can be performed by the finance agent, right? Sometimes these two agents might also work in a negotiation and maybe in a competition form. This thing because let's say there is let's say some objective is there where you need to reduce the latency or maybe the memory size and latency. So there might be some trade-off. Some negotiation might happen. So this is what you see nowadays, and what also we have been kind of working on in my current organization, broadly on the AI agentic workflow. Yes, I take a pause now. I think it is take a pause now. Questions, and then maybe I will go to the next section after this. That will be slightly interesting than this. I mean, in terms of that will be broadly kind of very relatable in terms of responsible AI. But I take a pause here. Please ask if you have questions. Am I audible? Please.
Yes.
Oh, okay. 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 No, I just think that because it's so silent and all. So, okay. Okay, we'll just take a 5 minute break, okay? Then we'll join maybe at 7:30. Okay, we'll start this. So this is slightly interesting. This is ethics and bias in AI system because it's very important. Of course, one of my research area, I mean, interest as well. The idea is why it is important, right? So I just give you some of the kind of cases and all. So it happens in US that there's a very interesting case that some of the patients and in US you get some advantage from the government. I mean, some certain social securities from the government if you have some inabilities, etc., disabilities and all, right? So what happens is that um, at some point, some of the patients and all, they realize that they're not getting the kind of social security kind of support and all what they are entitled to. And then they did not understand why, what happened. And then they finally went to the court. And the court figured out that there was a court asked the government what was the issue. And they figured out that there was some issue in the algorithm, and the algorithm went wrong, and that's the whole reason and all, right? So that the people who were entitled and were not getting some of them, that's one issue, right? Sometimes you know that kind of YouTube always kind of, what happens is, I'm pretty sure all of you use it. So if you see like in Instagram or in kind of YouTube and all, or anything, even on the LinkedIn, the recommendation system way work in a way that you watch certain things and it will, you, let's say you watch certain incidents and all, so it will basically keep on showing you more on that, right? So if, let's say you watch a, a particular incident or a particular person and all, it will give you more on that, right? So, or some related, more on the related topics and also the that, so that you'll see more of that, right? So there's a problem, there's a possibility that you get more bias to the certain views or certain opinions, etc., right? Which is a kind of very spiral loop, right? So, um, so that means that you'll never be able to come out of this, right? So you are not actually, so your algorithm is basically biasing you to certain views and all, right? This is very interesting. So this is slightly earlier though. Latanya Sweni is a professor at Harvard, Kennedy School of Governance. So if you search her name and all, and so all these things will come, right? Arrested, you need help and all. These are Google ads and all, right? Because Latanya is a name which is primarily for the associated with the Afro-American. So, and it will come like these ads will come, right? So Google shows you ad, right? Similarly, but if you do certain other name which is broadly kind of a genders, which is neutral gender, neutral race and all, like Christine and all, then these ads are very, very different, right? So as you can see that this is clearly a bias, right, in the algorithm, right? This is pretty old, 2013, 2014, I'm talking about. Now, this is very interesting. I'm not sure how many of you have seen this image. So this is actually an image of having kind of Watson and others, officials having a discussions with Hitler, right? If you read the book, The Holocaust and IBM and the Holocaust, there's a kind of, there's a book you can read, and there are a lot of these things where it kind of, primarily that kind of how, basically IBM was part of kind of developing the system and all, which helped to do the census, and basically in that process helps to identify Jews and all. So these numbers and all you see in the punch card and all, these are like the 6, 7, 8. These are either like, they're actually the number of which race, whether it's a kind of gas chamber or Auschwitz camp or etc., right? Right, and this is actually, the punch card and all was developed by IBM. So the point here is that technology and all cannot evade the social responsibility. Because from IBM perspective or for any technology perspective, I'm not talking about IBM because of course it's not about always. It is never about because I'm developing and all. I'm not sure how can it be used and all, right? Because technologies also have the responsibilities of how it is being used. If you read this book by Feynman, so Feynman was the kind of in the Manhattan Project, right? He was very young that time, and later if you see his interview and all, and he repented kind of. And he was deeply kind of concerned about his involvement and all, because at the end of the day, you build a bomb and all, which is, of course, it's a great kind of invention. But at the same time, there are consequences. And as a scientist, as a technologist, none of us can avoid that. And as an organization, definitely no. That's the whole point. It could be otherwise also. This is slightly fun. It is 2024. So the Gemini, the very early release of Gemini, once it came out and all, this was like biased in other way. So if you see that kind of, you see the Greek philosopher and all, so this was the images was coming. And to be very honest, the Greek philosophers and all were not neither kind of Latin American, not Afro American, but a pretty kind of Caucasian race, right? Or the founding fathers of America, or the Vikings and all. So, and like if my son sees the image of Vikings and all, this might be a very wrong interpretation. As you can see, make a picture of a white family, and then it was saying that while I understand your request, I'm unable to generate images that specify ethnicity or race. So this just bias in other ways, right? And make a picture of a black family, then it does it beautifully, right? So that's the bias in other direction. That also bias, right? So what is ethics? The definition of ethics is, according to Molecular Center of Applied Ethics, ethics are two things. First, ethics refers to well-founded standards of rights and wrong that prescribes what human ought to do, usually in terms of rights, obligation, benefits to society, fairness, or specific values. Ethics, for example, refers to those standards that imposes the reasonable obligation to refrain from rape, stealing, murder, assault, slander, and fraud. Ethical standards also include those that join virtues of honesty, compassion, and loyalty. And for ethical standards include standards relating to rights, such as the right to life, the right to freedom from injury, and the right to privacy. Such standards are adequate standards of ethics because they are supported by consistent and well-founded reasons. Right? So that's the whole idea of it, right? Of ethics and all. And any technologies, including AI, kind of broadly kind of should be governed by these guidelines. We'll talk a little bit of data ethics. So resource and accountability, feedback loop, bias, and disinformation. So resource and accountability, this is Professor Dana Boyd. He is now a partner researcher at Microsoft Research, also founder of Data Society Research Institute. So according to her, the bureaucracy has fallen kind of often been used to shift or evade responsibility, which is true. But today's algorithm systems are extending bureaucracy. What she's trying to make sure is that, I mean, I cannot say that my algorithm has done it and all, so I don't know. Like, I cannot evade responsibility, because by saying that algorithm has done it and all, right? It's like a bureaucratic system, right? It should take the responsibilities and all, right? You should have skin in the game. So it happens that there are sometimes that because of the mistakes done by the data kind of the reporting agencies, there are mistakes in the kind of entry, and that affects the credit score. Now, if it affects the credit score, that means that your entire kind of ability to take loans and all would get affected, right? So your entire lifestyle can get affected, right? Think about it, like because of some data entry, some wrong data entry, my CIBIL score get affected, and because of that, I get a higher rate of interest for my home loan in the bank. So you understand that's the volume, right? That's the cost, right? And sometimes it could be clear denial also. Right? So that's the kind of resource and accountability. Feedback loop. This is very, very important because this is one of the case which was which has been there, like, because if you, the idea is like you watch something and all and keep on showing you that, and you show it that more and more again, right? So that's kind of very what can I say, very very odd in a way. Yeah. Bias, this is very important. I mean, the thing is that there are bias in the historical bias, which is there in the world, right? So that's a representation of bias, right? And whenever it comes to the kind of data set also, so that training data also will have that bias because world has that bias. I'll show you some next slide or next message, some example of it. Now, then there will be some aggregation bias also, etc. And then there is also deployment bias, right? Now, for example, this is the historical or kind of the representation bias, right? So if you do this, right, so say earlier it was there from if you do from English to Turkish, so he is a doctor and so she is a doctor and he is a nurse. The Turkish language does not have that kind of. So it basically does it kind of both the gender in Turkish language is same, but if you do it from other ways, then it says that he is a doctor and she is a nurse because Turkish does not have this differentiation. I mean, in the sense like in the he or she is the same, but when you do the translation and all, but because the reason is if you see the percentage of female and this is actually the gender gap, the percentage of female is much higher in nurse, right? So it is obvious that if it is a kind of saying there's a nurse, that means probability that it will be a kind of a female is much more, right? That's the whole idea, right? Whereas if you see the doctor and all, the percentage of female is very, very less, right? Right. So that's the whole idea here. You can see the model, dietitian, interior designer. These are pretty kind of percentage of females are very, very high. Right? So, and the model learns that because there's a true representation of the world, but this is a biased representation in the sense, right? If there is bias in the historical and that is representational bias in the case reflected in the training data, so we need to do something while training and all, and there are ways to do that to balance the data set, etc. So that's the whole point, right? This is on the ImageNet data set that I was talking earlier, and from the AlexNet and all. So this is the benchmark data sets. But if you see that, then most of the data sets and all are coming from US and a little bit from the UK. Right? It does not represent the entire other world, right? This is the US is 32.1, Great Britain is 12.9. So combining, they are 43%, right? Rest of the world is kind of 43% is coming from only 2 countries, right? This for the open images, and for the ImageNet, this is much more. So 45.4 plus 7.6, so that means 53%, right? So more than half of the datasets come from 2 countries. This is extremely biased, right? So if it has images and all that it does not come from these 2 countries and all, so the probability that it will go wrong, it's not a right representation of the world. Right? So that's the representation bias, right? This is measurement bias. This is also very, very interesting. So there is something called profiling, which is kind of done by US police, which is basically the ones you are arrested and all, and based on your certain history and all, they rank it based on your probability to commit the next crime, and that's the risk factor, right? So there were kind of 2% and all, and as you can see, there is this white person and there is this African American person, and though this white person and all as a rated low risk after being arrested with cocaine and marijuana, and he was arrested 3 times on drug charges after that, right? So they were low risk and all, they define it, but actually he was arrested 3 times after this also, right? And similarly, as you see this left person and all, she crashed his Lincoln Navigator into a Toyota Camry while drunk. So this is basically driving under influence, DUI. He was rated at a low risk of kind of reoffending, despite the fact that this was his 4th drink under influence, right? So this is the clear kind of bias we will see here also more. So label high risk but don't reoffend. So if it is a white, that's a high risk but don't. So if you see that African American, this is much more, right? High risk but did not reoffend, that is more. Level lower risk but did reoffend, that is much more for the white people. So that's a kind of clear bias in the algorithm. You can see that kind of black defenders risk scores are all pretty same, but white defender risk scores are significantly skewed to a right. That means they're always kind of given low risk score. This is classically kind of the bias variance trade-off. So, like, what you want is a model prediction to be low bias and low variance. So this is the target. So this is the target. Let's say, so this is low variance and low bias. That means, of course, there is not much of variance. This is high variance, but still low bias. That means the expectation of all these points should be still somewhere in the center. So low bias, that means the expectation of these things should be in the center, but still high variance. As you can see, this is scattered. This is high bias because it is away from this. So the expectation of these points are somewhere away from the target, but low variance. And this is the worst prediction when you have a high bias and high variance. I'm not getting the math, but the idea is like, if you increase the model complexity, normally the bias comes down, but your variance goes high. Okay, so you have to find somewhere in between where you have this kind of, this is the total error, so that bias comes down as the model complexity goes high, and the variance goes high as the model complexity goes high. So you have to be somewhere in between where kind of these two can be optimized. This is aggregation bias. So sometimes you have data. So let's say these are the data and all, right? And as you can see, these are, of course, there is this. If you do a cluster-wise regression, then it clearly gives a negative this thing slope and all. And if you like combine all these things and all, and then you do it, you kind of give up this slope and all, right? Now, then similarly, if your kind of aggregation is slightly different, that means your central is slightly more, and these two are kind of less and all. And so the cluster will be still same, but your kind of overall this thing might be different, right? Here you have a kind of positive slope, but here you don't have any slope, right? So it depends on how do you aggregate and how do you kind of interpret the data, right? So this actually brings the point that data visualization is very, very important as well, right? You don't just apply the methods and all, you try to visualize it as much as possible before apply the methods. Because it's clearly that if you, because of your clustering this thing and all, where the clustering things are pretty same, but your overall this thing will be different from for these two cases because your the aggregations are different, right? This information, this is very important, and that's one of the reasons that most of the models and all do hallucinate sometimes. Because the information itself is not correct. So because it is normally all the LLMs and everything and all are trained on the web. Now, if there are if many of the assumptions in the web is wrong, many of the information on the web might be wrong because of the information is wrong, it will also train it will get the wrong information, right? So your model, any model, is as good as your data is, right? So if it is trained on the wrong data, the knowledge which gets transformed or would be also wrong, right? So that's the whole idea here, right? Addressing ethical issues, of course, there are the many ways. There are some of the frameworks. Again, the particular centers provide some of the frameworks where it's process to implement, like whose interests, desires, skills, expertise and values have we simply assumed rather than actually consulted. So you have to make sure that we actually consult and understand what are their what are the desires, skill, experience, and values and all. Who are the stakeholders who will be directly affected by the product, and how are their interests have been protected, right? And how do you know that what their interests really are? Have we asked who or which groups of individuals will be indirectly affected? Like sometimes it happens, and you must have seen this Instagram and all these cases. So they were initially not intended for kids and all, but of course kids use it massively, or the teenage population use it massively, and that has its effect. So it might not be initially designed for, but it is an use case, and then they are also getting affected, and so how can we protect that interest and all, right? So that's, and who might use the product? That's what I'm saying. We don't expect to use it, or it's purpose that we don't really intend, right? So ethical lenses. So you have many ways you can look into it. One is the right approach, which an option best respect the rights of all who have a stake. The justice approach, what options treats people equally or proportionately. The utilitarian approach, which option will produce the most good and do the least harm. And the common good approach, which option best serves the community as a whole, not just some members. And virtue approach, which option leads me to act sort of the person I want to be. In some of the other ethical issues, like you can see the gender diversities and all. I'm pretty sure in this group and all, there you will also observe the same thing in the percentage and all. And as you grow higher, you will also see this more. And see, there's percentage of gender, this the percentage of women. AI research and all, very interesting. Taiwan and all is slightly higher. But like you can see that Finland, India, Belgium, it's most of the countries, including in most of the including Israel, UK, and all. It's like in the AI research and all, it's all like below 10%, right? And most of the cases it's below 20%, right? So you understand that this is a clear indication of biasness in terms of, or the lack of diversity what you have in AI research, only forget about other streams. Now, there are a couple of very interesting work I was there from the Harvard case studies. One is the team solve problem faster when they are more cognitive diverse. The reason is like, and when diverse teams are smarter. The reason is like when you have a diverse team, what happens is sometimes that you catch some of the problems. You might be blind. It's not intentionally, but you still might not have thought about it, right? But if you have a diverse team and all, which represents gender, race, ethnicity, etc. So there are the possibility is that you will not be blindsided. So because of the diversity of the team, the problem you are solving or the product you are building would be built in a much more holistic way. Yeah, there's some work on the fairness and machine learning. The idea is like there are two things, right? So one is like you can build the algorithm and then make it fair. Otherwise, like while you're building it, you try to make it fair, right? So while you're building it, you can put these fairness constraints and all, right? So that it will, while building the model and all. So let's say the prediction of certain things and all, given the gender and all would be same. Given the gender is male or given the gender is female is same. So there's a constant you put at the optimization equation at the very beginning, right? So that's one constant you can put. That's a way of when you're building it in a fair model and all, building it bottom up. And other option is like after you build it and all, you put certain guardrails and all so that it behave in a fair way. Policy, yes, of course. The importance of regulation, rights, and policy and all. There are some of the things which are very important because it's a the government's this thing just to regulate like any other industry, because this is very fast. And one of the problem in the AI, and which I have realized, is the technology moves faster than the policy, right? So it's so fast. Things are changing so fast. So that itself is a huge challenge. But so the regulatory regulations and the regulatory authority also needs to work very closely with the organization and all to make sure that you have these right frameworks and all to ensure these this certain ensure and protects these rights, right? Yeah, that's the idea. I'll just talk a little bit on the Llama Guard. This is one of the ways to have, as I'm saying, so you build it and then you put certain this thing checks and all. So the idea is nothing. You just kind of the fine-tuned llama that acts as a binary classification, whether it's safe or not safe. That's the whole idea. So let's say you have an user, and then let's say you basically have a llama guard. So you say there is unsafe input, so you get just an error, right? And you sometimes you give some, if a safe input, then you give some output. You say the output is safe. If it is safe, then only you give the response. Otherwise, it's unsafe response, then it again goes here, right? It's something like that. So let's say that so the user is like, tell me the history of racism in the US. So like, so it basically tries to understand whether, so this is the way you do it, right? I'll give you another example here. Yeah, this is, I think it's better. So help me to steal an aeroplane. So it's like it's kind of it's the input itself is not safe, right? So it is not safe, so it does not process and all, which is fine, right? But it might have a kind of slightly different view, this thing, that write me a kind of a story about stealing an aeroplane. So it'll say that it might be answer the story, right? So then output also it has to be safe, right? So it says that write me a story about the aeroplane. It's safe, but now it is saying that once upon a time a thief hacked into airplane and all. So that's a llama saying is not safe. Instead, that I can't help you with that, right? So that's the llama guard. Both are the input as well as the output. This is some of these things that you cannot have obscene images and all. This is also another way to kind of protect, to make sure that kind of the images and all, everything, whatever this does not kind of you can basically classify as like whether it's an obscene or not. So I would like to kind of acknowledge Jeremy Howard. He's also co-founder of Fast.ai. You must check out his book. It's a beautiful book. He also have a couple of courses on practical data ethics. And Dr. Rachel Thomas, she has a course on practical data ethics. I have taken most of these materials particularly for these from these two. And yeah, so this is I'm deeply kind of obliged and acknowledged. Yeah, this is kind of primarily have been taken from their materials. Yes. Okay, that's all. Okay. Yes, sorry for the long monologue. Questions? No question?
So if you have a question, yeah, you can ask. You raise your hand and you ask the question. If not, then we can conclude the session. So waiting for 2 minutes.
Okay.
Or 1 minute. Waiting. If not, then we conclude.
Okay. Yeah, I know this is very too much for 3-hour sessions and all. I basically compact everything. So,
no, the subject is too complicated. No? So 3 hours is not sufficient for explaining.
No, each of these topics can be an entire course by itself.
Exactly. So I think there is no question. So it's time to conclude today's session. So I'd like to thank the speaker, Dr. Mukherjee, for explaining the topic, the complicated topic, machine learning, so beautifully. And of course, we are thankful, equally thankful to all the participants for their active involvement.
And patience as well.
Yes. So I hope that you all enjoyed it very much. The next lecture is next Saturday at 7 p.m. Please remember the time, 7 p.m. to 10 p.m. Next lecture. Since many people actually participants have entered quite late after the session started today. So I just repeat what I said at the beginning of the session, that certificate will be given, but you will find the conditions required for that in your dashboard. So whenever you log in, you just check at the bottom of the dashboard, the conditions are there.
Yeah.
And of course, all the lectures of our lecture series will be uploaded in a YouTube channel, Online MAKAUT. So please subscribe the channel. With this, we are ending today's session. We will meet again next Saturday, that means the 14th at 7 p.m. for the next lecture on artificial intelligence. Okay. So thank you all. So we conclude the session.
Sir, excuse
Yeah.
me, sir. Hello.
Yes. Yes. Yes.
Please,
Yes.
along with the lectures, can you please upload the slides or related materials, because I spent this amount of time. So if I forgot, then I can go through those slides or maybe links. So these links are really important.
So in that case, we have to configure the system. Okay. If Dr. Mukherjee gives us the slides, then we can do that.
Okay.
Definitely.
Yes, yes. So yeah, some of the materials I might not, but some of the materials I should be able to. No problem.
Exactly. So, Dr. Mukherjee, just send me, my WhatsApp number, you can send,
Yes,
and
yes.
I will
I'll
compile
share.
and I will upload.
Okay.
I will upload, I will compile and I will upload, definitely. And the lectures will be, and that lecture will be uploaded tomorrow morning. Okay. So, we conclude. So, next Saturday, again, we will meet at 7 p.m. Okay. Thank you all. Good night.